Hello, my name is ZulAziz PresenterID number 5. Today I will be presenting a paper titled Mutual Inductance Estimation for Asymmetrical Coupler with Multiple Transmit Coils. In the coming slides, I will detail out the techniques we use to estimate the mutual inductance of a wireless coupler made up of 6 symmetrical transmit coils and a miniature receiving coil with large transmit to receive diameter ratio of 15. By definition, mutual inductance is the phenomenon in which a change of current in one coil causes an induced EMF in a nearby coil. It is a topic which has been well documented and frequently discussed in wireless power transfer. So how can it be evaluated? Numerous contributions have been made in the literature in relation to the problem of mutual inductance calculation for coaxial circular coil. These contributions have been based on the application of Maxwell's formula, Newman's formula, and the Biot-Savart law to obtain a general expression, followed by solving analytically or semi-analytically using the elliptic integrals, Lagrange polynomials, or Bessel functions, which unfortunately can be quite daunting to deal with. In addition, this derived expression had limited applications since they have been derived for the case of a symmetrical coupler. A survey of past literature will also reveal that the greater part of this work was concentrated on the mutual inductance between an inclined filamentary circular coil and a thin wall solenoid, or between two inclined thin wall solenoid. We began with the calculation of the mutual inductance between multiple transmit pairs by finite element method over Maxwell's relation. The results were verified against experimental result. Triple Helmholtz coil pairs were coaxially arranged to provide a uniform coverage inside a 10.6 liter acrylic cylinder, where the coil geometry and spacing has been optimized in our previous study. Despite having similar geometry, each coil will have different inductance because of mutual inductance with nearby coil. Next, the mutual inductance between the transmit and the receive coils were determined as follows. The transmit coil's magnetic field were numerically computed by finite element method over standard Maxwell equation. The mutual inductance was obtained by evaluating the loop integral of the magnetic vector potential over the receive coil. Finally, the result was experimentally verified. For mutual inductance of multiple transmit coils, pairing effect for coil 1,6, coil 2,5, and coil 3,4 were observed and expected, since the innermost coil were nearer to the neighboring coil above and below it, compared to the outermost coil, hence would experience more coupling. The discrepancy between the result calculated by finite element method and experimental was about 5%. Due to homogeneous multi-turn coil used in the finite element model, while in the actual experiment, a least wire was used to minimize the skin and proximity effect. The skin effect was apparent in all 6 transmit coils, as evident from the simulated series resistance curves, showing an incrementing trend at around 100 kHz and upward. These effects, however, were negligible in the actual experiment, because the strand diameter of the least wire used was smaller than the typical skin depth of copper. For the mutual inductance of an asymmetrical coupler, where the size of the receiver was much smaller than the size of the transmit coil, the discrepancy between the result calculated by finite element method and experimental now was about 3% only. This is also due to the homogeneous multi-turn coil used in the finite element model, while in the actual experiment, a least wire was used to minimize the skin and proximity effect. Error was smaller due to the large transmit coil diameter compared to the receive coil. In conclusion, we have demonstrated that the combination of finite element method with simple integral arithmetic can be used to quickly estimate the mutual inductance of 6 symmetrical transmit coils at good agreement with the experimental result. The techniques can also be extended to an asymmetrical coupler with large transmit to receive diameter ratio. Knowing the mutual inductance value One can now precisely tune the Class E amplifier to operate at the intended specific switching frequency. The method proposed herein can be applied to a plant-scale slurry photocatalytic reactor for the treatment of petrochemical wastewater. With that, I concluded my presentation and will be happy to answer questions if any.